Offline.
All right. Welcome to.
Offline. Oh, okay, sorry.
Welcome to the 7th and final session of this module. So we've spent the last, I was going to say 7 weeks. It's been quite a lot longer than that, but 7 sessions talking about writing our own structs and classes in C++ and how we go about doing that. And so today's going to be the last session on that, and in a minute I'll talk about what we're going to cover today. So, as you know, what we're doing this year is that we're doing a sort of split arrangement. So this track is every other week, and we alternate with a beginner's track covering or recovering what we did last year, aimed at people who missed us starting out last September and want to still want to join in with our classes. Sorry. So in 2 weeks' time will be the next class for this track, and it won't be me. We're going to have a new tutor, a guy called Alex, who you might have seen. He's not here tonight, but he has been to a few of these sessions. So he's going to be telling you all about the C++ standard library. So I think the name of the module is Getting to Know the Standard Library, or an Introduction to the Standard Library, something along those lines. But that's what he's going to be telling you about for about the next six sessions. So sort of, I think roughly till Easter or a bit past that. So yes, that's going to be really good. You're going to have a bit of a change. It's not going to be me, someone else standing at the front. I'll still be here. I'll be at the back, offering helpful advice the way Ollie does usually when he's in these classes. So unfortunately, you're still going to see my ugly mug, but I won't be in front of you. I'll be hiding at the back. Yes, so that's the plan. But this is a standard slide all about how we like you to join the Slack channel. But I'm sure most of you have seen this many times before. But if there's anyone who's watching on YouTube or whatever for the first time, we sort of make use of this Slack chat app. There's a Slack channel for discussing the C++ language, and we have our own chat room in there, #CPP London Uni. So if you'd like to join us, if you'd like to chat to us, you can go to that URL that's on the screen, slack.cpp.al. There's a little web form, pop your email address in, and then you can come and join us. So as I say, we've got our own room in there, just #CPP London Uni. There's another one which is #learn, which is a really great resource if you're learning C++, if there's something you're not sure about, if you're getting compiler errors and you don't know why, then #learn is a really good resource, because it's full of learners from around the world, but also a lot of experts in there who will be able to diagnose your problems very quickly. So yes, you're all encouraged to go and make use of that. Oh, I've made look at this. This is slide 3, and I've made a mistake already, because I said last week. It wasn't last week. It was 2 weeks ago. I haven't got used to this 2-weekly thing yet. But bi-weekly, yes. Last session anyway. Oops, sorry, too far. No, much too far. There we are. So last week we talked about explicit constructors, explicit keyword, what that does, and we also talked about member initialiser lists. This week, well, first of all, I have a bit of a confession to make, as you might be able to hear, or you might know if you were involved last week with the other session. I haven't been very well the last few days. Ollie is off sick tonight. I think it's just like a C++ London Uni lurgy going around. That's why Tom's leaving. It's nothing to do with anything else. He just doesn't want to catch nasty germs. But so yes, one of my confession is I haven't really had as much time to prepare for this session as I'd like to. So I did want to go and talk to you about copy assignment operators as well, but I didn't quite get far enough into the preparation to do that. So apologies, I haven't quite done just that last little bit, but hopefully we'll still have enough for tonight. And by all means, I can tell you all about copy assignment operators. I just don't have the slides for it. So, maybe I can do something on the board or something. I don't know. Oh dear. Okay. Oh yeah, and the other thing to say is that even if you are familiar with other languages that work in similar ways, Java and C# and Swift and so on, but Java and C# in particular don't really have this notion of destructors and copy constructors in quite the same way that C++ does. So even if you are really quite familiar with these other languages, you might still learn a bit from tonight's thing about destructors in particular. I hope. Okay, so who was here for the session 2 weeks ago, for the last one of these? Most of you. Well, as usual, I'm going to, because it's quite a long time ago and I need a refresher as to what we were doing. So I was just going to go very quickly over what we were talking about before, because I think it's handy to do a little quick bit of revision. So first of all, we talked about implicit conversions, and this is what happens when you call a function whose parameter types don't exactly match the arguments that you supply to that function. Right? So if we have a function that takes a float, we are permitted by the language to call that function using an int, because int and float are in some sense compatible types. And specifically, it means we can convert an int to a float. So what happens is when we call that function, the compiler is going to automatically do the conversion for us. Automatically, kind of behind the scenes. Do it implicitly. We call this an implicit conversion. And in fact, the compiler tries really, really, really hard to do these implicit conversions for us. Tries really hard to make you happy. It says, I know you want to call this function, and I'm going to do whatever I possibly can to let you call this function. I just want to make you happy. And one of the ways it does this is, well, the terminology is it forms something called implicit conversion sequence. But what it really means is that it will look at the constructors of the target type. So you imagine you've got like a sort of source type, that's your argument, and you've got a destination type, that's what the function actually accepts, right? And then it tries to convert from one to the other. And one of the ways it tries to do that is by looking at the constructors of the target type. And if there are any... Hello? What's happened there? Nope. Well, that was weird, wasn't it? Try again. It will look at the constructors of the destination type. And if there are any constructors which take a single argument of the source type, then it will transparently, behind the scenes, use that constructor to do the conversion from the source type to the destination type. Right? Implicit conversion will automatically use these single argument constructors. So here's our friend the circle class again. As we have been seeing, we've seen it in many guises in this module. Sorry. So we got a constructor that takes a float. We got that get radius thing. It's not really relevant to this example. The important bit is we have a constructor that takes a float. And then we've got a function called print radius, which accepts a circle, or in this case a reference to a circle, and calls the get radius function in order to, well, get the radius of the circle and print that out. So hopefully at this stage this is kind of familiar. If you're not sure about this colon thing in the constructor, don't worry, we're going to talk about that in a second. But let's have a look at using this print radius function. Well, first of all, we can create a circle, in this case with a radius of 4.2, and we can call print radius using this circle thing that we've just constructed. And this is going to work exactly as you would hope and exactly as you would expect. This is going to print out 4.2 followed by a new line. So this is fine, this is good, this is what we want. In fact, if we want to, we can do it all in one step. We can construct a circle sort of in the function call, if you see what I mean. And again, this is going to do roughly what we expect, or exactly what we expect. It's going to print out the radius 4.2. All good, excellent. This perhaps is a bit less good. This is a bit weird. So this works. We can call print radius and just pass a float. And the reason that this works is because of implicit conversions. So what's happening is the compiler is saying, okay, you want to call a function print radius and you're passing me a float. Well, I've only got one candidate for print radius. It's this guy. If we had multiple overloads, the situation would be different, but in this case, we've only got one candidate, and it takes a circle. So the compiler says, is there any way that I can convert this float that you've given me into a circle? Because I really want to make you happy. And it can. It can convert a float into a circle by using the circle constructor up here. So behind the scenes, the compiler inserts a call to the constructor. It constructs a temporary circle and passes that to the print radius function. It implicitly converts a float into a circle. And the end result is that you can call print radius with a float, which is kind of weird. And in fact, it's even more weird than that, because it doesn't just work for floats, it works for ints. And this is even stranger, because what's happening now is the compiler is saying, okay, well, right, you want to call print radius, I've only got one candidate, that takes a circle. I've got an int. How can I go from an int to a circle? Okay, well, circle's got one constructor that takes a float. Can I convert an int to a float and from a float to a circle? And yes, it can, because it knows how to convert an int into a float. That's like built into the compiler. It knows how to convert a float into a circle, because it can use the constructor. And so it goes through like two steps. This is why we call it a conversion sequence. It chains together these transformations because it's really trying really hard to let you call the function. And like, to me, this is just kind of mad. I could sort of understand the floats thing, but yeah, using an int to call this constructor to call print radius is just very strange and very weird, and 9 times out of 10 is not what we want. Unfortunately, we can avoid all this by using the explicit keyword. And by putting the word explicit in front of our constructors, it prevents the compiler from using that constructor as part of one of these conversion sequences. And this is good and this is desirable. As I say, 9 times out of 10, implicit conversion is not what you want. There are rare circumstances where it can be handy. You know, I gave an example last time of converting a string literal into a standard string. Well, that's kind of a handy implicit conversion. It means we can, if we have a function taking a string, we can just write something in quotes directly. Well, that's kind of handy, but most of the time it's surprising and unexpected. And you know, that case was relatively benign, but can lead to situations where you get function overloads being called that you really don't expect. It's a bad thing. And so get into the habit of writing all constructors which take a single argument with the word explicit in front of them. Right? That should just be kind of automatic. And only remove the word explicit if you are absolutely sure that implicit conversion is good and desirable and something that you want. Right? This is one of the instances where C++ basically got the defaults wrong. Right? Implicit conversion isn't like always bad. Sometimes it's what you want, but most of the time you don't. So most of the time we want to put this word explicit in front of our constructors. Single argument constructors. You can put it in front of other constructors, it does no harm, but it doesn't really do any good either. It's only really relevant to constructors which take a single argument, because those are the ones that can form an implicit conversion sequence. So this slide is exactly as it was before, with one little change, one extra word, and that's the word explicit in front of the circle constructor. And what this means now is that this constructor cannot be used for an implicit conversion. So if we now look at our calls to these functions again, well, calling print radius with a circle that we've already constructed, this is going to work just as it did before. This is still going to work. This is all good because there's no conversion involved here. We have a circle, print radius expects a circle, there's no conversion, there's no need to call any constructors. This is going to work just as expected, just as we want. And we can still directly construct a circle as part of the function call because, as I said before, we have a circle, function's expecting a circle, no conversion, no constructors, all good, all fine. However, this time, if we try and call print radius directly with a float, it's not going to work because the compiler is going to try and do the conversion, it's still going to try for us, but it's going to say, how can I do this? Well, I could do it by calling this constructor, but this constructor is marked as explicit, so that rules it out. I'm going to ignore it, pretend it doesn't exist. So it will not use this constructor, therefore it cannot form any sort of conversion sequence, therefore it's going to give you an error. And the error will probably say, oh, I kind of wanted to use this constructor, but it's marked as explicit, so I just ignored it. So this is good now, this is better. Because calling print radius, like what is the radius of a float? Like it doesn't really make any sense. And of course, since we can't do it with a float, we can't do it with an int either. So this is good. And the takeaway from all that is whenever you have a constructor that takes one argument, put the word explicit in front of it. Even if you are not fussed about all of this stuff about implicit conversions, trust me, one day it will bite you and you will be surprised and you'll go, what is going on there? And all that confusion will go away if you just remember the kind of rule of thumb, except in special circumstances, always put explicit in front of single argument constructors. And in our rapid fire recap from a couple of weeks ago, the second thing we talked about in that session was member initialisation. So one of the perhaps most important thing that a constructor does is to ensure that all the member variables of a class are ready for use. It establishes the invariance of the class, as I was talking about way back, like last year. And C++, for various reasons, has a very strict rule that by the time control of our function, control of our program reaches the body of the constructor, all of the member variables have already been constructed, right? The order of constructing things is very strict, very well defined. C++ constructs objects by, well, first of all, the base classes, but we won't worry about those yet. We'll talk about those in a future session. But then it initializes your member variables from first to last in the order that they are written in your class. And only after it has done that does it run the body of the constructor. That's the bit between the curly braces. By the time we reach the body of the constructor, all of the member variables are there, are constructed, are ready for use. It's important to remember. Another way of putting it is that the constructors for member variables are done and finished by the time we get to our constructor body. So if you use a statement like, as you're about to see on the screen, radius equals initial radius in the body of the constructor, which is how you might do it in, say, something like C#. That will work in C++. But this is not constructing the radius, this is assignment. This is overwriting the value that is already there. There is already a value in the radius member by the time we reach the constructor body. And what this statement will do is overwrite the initial value. So let's have a look at our friend circle again. What this is going to do, note that I marked it explicit because it takes one argument. So this is how you might sort of, you might kind of naively write the circle constructor as you want to say, okay, someone supplied me an initial radius. I want to set my radius member to whatever that is. So all I'm going to do is in the body of the constructor, I'm going to set the radius equal to initial radius. And this is going to work, but it's doing a bit more than is necessary. Because by the time we reach the body of the constructor, all of our member variables are initialized and ready for use. In other words, the compiler has already initialized radius with the value 0, and all that's happening in here is you are overwriting that 0 with whatever the value is. Now, for something like a float, that's really not a big deal because like floats are really cheap, simple types, like it's all built in. That's not going to make a big difference in the runtime of your program, right? It's like one extra CPU instruction or something. It's not a big deal. But it might be a big deal if instead of a float, this was something that, like say, allocated memory in its constructor. Because then the compiler would be allocating some memory, which is quite an expensive operation that is like time consuming. Has to go away and like ask the operating system, can I have some memory? That takes time, things get locked. It's like quite a complicated thing to do. So if this allocated memory, and then you immediately overwrite that in the constructor body, it means that we have to allocate that memory, then immediately throw it away again and get some new memory in order to set the, well, say initial radius, the correct initial value. And in fact, it's even worse than that because there are some types which don't have a sort of valid default state, if you like. If we have a member variable that is not default constructible, and we don't supply one of these in-class initializers, then we're just going to get a compile error. It's simply not going to work. And the solution to all of these problems is something called member initializer lists. And a member initializer list is a list of initial values or constructor arguments for each of our member variables. And it also applies to base classes. Again, we're going to talk about those in a future module, but the syntax is exactly the same. Base classes appear in your member initializer list as well. And the member initializer list is a bit weird because it appears between like the signature of your constructor and the body. So usually with a normal function, those two things, the opening curly brace appears straight after you've written the function signature. But with constructors, with member initializer lists, the member initializer list appears before the opening curly brace of the constructor body. I'll show you what the syntax looks like in a second. And yes, just a reminder, by the time we reach the constructor body, all of the member functions have already been constructed. Oh yeah, we've got a new example this week, that's fun. So imagine we've got, we're writing a game, player character, it's got a name, got a weapon. In fact, why don't I just show you all the code and then we'll explain it. So we're writing a game, we've got our player character. Character's got a name, it's got a health value, and the character wields a weapon, right? This is appropriate for whatever number of games you can imagine. But so we've given our player character class, in this case, two different constructors. And the first constructor we're imagining is perhaps when you start a new game. So when you start a new game, well, the player's probably already inputted their name as part of like the startup. So we're going to create a new player character object. We're going to pass the name that we want to use. And then in our member initializer list, that's this thing with the colon between the constructor signature and the constructor body, which is these empty curly braces here. We're going to use this member initializer list to initialize the members of our class. So we're going to initialize the name, our name, with the name that we were given. And we're going to say that, okay, the initial weapon that the player gets in this particular game, they start off with a sword. Maybe they upgrade it to like a broadsword or a longbow or whatever later, but they start off with a sword. We've also got a second player character constructor. Imagine this one is for like when you load up a save game. So when you load up a save game, you might have a different health value that was saved. You might have a different weapon that you've collected somewhere along the game. So in this case, we need to initialize all three of our members from the constructor arguments that we were given. The name, the health, and the weapon. Now this syntax of repeating like name brackets name, health brackets health, this is a bit strange. And I've done it in this way quite deliberately just to show you. It's not necessary, it's usually advised that you don't do this, but I just want to show you it just so that if you do see it, you kind of know how it works. Is that in the initializer list, things appear as our member, and then either round brackets or curly braces, and then the second instance of name refers to the argument. So this first one means our member, that's the thing we're initializing, and the second bit is the one we're initializing it with. Now, again, as I say, it's not usually recommended to have the arguments be the same as your member variable names. This is kind of bad style because, like I say, it looks a bit weird and it's not necessarily obvious at first glance what exactly is going on. But yes, as I say, it works, and if you do happen to see it, that's what is going on. The first thing, the first bit in the initializer list always refers to the member variable name, and the second part, if it happens to have the same identifier, then it refers to the argument we were given. One interesting thing is that in this first constructor, we haven't mentioned the health member. That doesn't mean that health is not initialized. What it means is that the compiler is instead going to use this value that we've given in the class body itself. So with the first constructor, oops, go away. With the first constructor, after the constructor is finished, the name is going to be whatever the given name was, the health value is going to be 100, and the weapon is going to be a sword. I don't know how to make this go away. But, yeah. You're about to raise your hand and ask a question.
Is it possible to change the round brackets, round name and curly brackets?
Yes. So for the vast majority of classes, whether you use curly braces or round brackets, they do exactly the same thing. The vast majority of classes. However, you remember I was talking about aggregates a couple of sessions ago. Aggregates must use curly braces. Okay, so you think, okay, right, so now I'm just going to use curlies all the time. Well, no, you can't have that rule either, because there are certain classes, including one very important one, which is standard vector, which do different things depending on whether you use the curly braces or whether you use the round brackets. So unfortunately, there is no hard and fast rule to say always do this or always do that.
So you have to be aware of.
You have to be aware of the thing that you are initializing and which one you should use, yes. So in this particular example, it wouldn't matter which one I picked. But if I'd had a vector member, then that would make a difference, yes.
Are these constructors private?
I was wondering if anybody would notice that. Yes, unintentionally, I should have had struct player character or put the word public at the top. It's a bug in the slide. So this is something I mentioned last time, and I just mentioned it there, is that there are three ways that a member variable can be initialized. Either it can appear in the member initializer list, and that's where it gets the initial value from. If it doesn't appear in the member initializer list, but it has an in-class initializer, which was the case for health on the last slide, then that's the value that gets used. And if neither of those things apply, then we're going to get what we call default initialization, default construction, if the class has a default constructor. If it doesn't, and it doesn't have either of these other two things, then you're going to get a compile error. Which brings us on to the last little slide, and it's something that's very important to be aware of when you're using these initializer lists. I mentioned it before, but I'm just going to reiterate. Class members are always, always, always constructed in the order that they appear. Okay? In particular, the order in which they appear in the member initializer list is absolutely irrelevant. Doesn't matter, well, doesn't matter at all as far as the compiler is concerned. And I showed an example last time, you can go back and look at that if you like. But there is a possibility well, not a possibility, it's a bug that comes up, used to come up quite frequently, is that particularly when people are using one member variable to initialize another one, that they get into this situation where they write things in the wrong order or in a particular order in the member initializer list because they want things to be initialized in that order, and they forget that the compiler ignores whatever order you put things in the initializer list. That is completely ignored. It doesn't matter, because the compiler is going to follow this hard and fast rule that the order in which your members appear in the actual class body itself, that's the important bit. So the rule that you should follow, the rule to remember, the takeaway from this is always write things in the initializer list in the same order that they are written in your class body. You're allowed to skip things if they're in class initializer or whatever, or default construction is fine. You're allowed to skip them, but you're not allowed to reorder them. And in fact, compilers nowadays will generally warn you if you write a member initializer list that lists things in a different order to what you should do. Right, so this is less of a problem than it used to be, because now compilers will warn you, but it is something kind of to be aware of. Oof. So I left you with a little exercise last time, just on using initializer lists. Did people do this? Who had a go at this? Anybody?
I have something, but
Okay, well basically I wanted you to add a constructor to the person class, which used a member initializer list, add a member initializer list to this person list constructor here, and then fill out as a sort of add-on, fill out this add person function that I've declared but not defined here. So my solution to that looks like this. We've got person on the left, and as you can see, we've added a constructor that takes two string references, and it uses an initializer list to initialize the first name and surname fields of this class. So this is kind of pointless, but like I say, I wanted you to have a bit of practice of writing initializer lists. On the right-hand side, it's a little bit trickier because, as I was just saying, vector is one of these unusual classes that behaves slightly differently depending on whether you use round brackets or curly braces in the initializer list. So for vector has a whole bunch of constructors, but it also has the facility to create a vector from a list of elements. And if you use curly braces, that's supplying what we call an initializer list. Don't confuse it with member initializer list. I know the terminology is terrible. I didn't come up with it. Right? What this is saying is this is a vector of one thing, and that one thing is the value person that we were given. If it was round brackets, that would try and find a matching constructor, but instead this just initializes the vector with one member, and we could add however many members we wanted in there, but in this case we only want one. So yeah, this was a little bit tricky, and I was kind of expecting that some people might use the round brackets and have problems and then have to go back and look at why that was. The other thing I wanted you to do was this add person function. There are a few ways that you could do this. I thought most people might try it. To start by constructing a person object and then placing that into the vector, and that's absolutely fine. It's a perfectly valid way to do it. There is a very, very, very slightly more efficient way of doing it, and that's to use this ImplaceBack function. And if you use C-line, you might see that sometimes it recommends that you should use ImplaceBack rather than pushback. What ImplaceBack does is, instead of, so pushback, we have an object, and pushback copies that object into our vector. ImplaceBack does something very slightly more efficient, which is it directly constructs a new object inside the vector rather than doing any copying or moving. It's kind of uncommon you're going to see a big difference unless you're adding millions of things to a vector in one go. But ImplaceBack is there. It was added in C++ 11. And the way that we use ImplaceBack is, so people, it's a vector of person. And because person now has a constructor, what we do is the arguments we supply to ImplaceBack are the constructor arguments of, in this case, the person class. So what ImplaceBack is going to do is it's going to call a person constructor that takes first name and surname. So this constructor up here, and it's going to call that, but construct the object directly inside the vector. Right, so it's kind of a minute optimization. But if you have wondered what this ImplaceBack thing does, then that's what it does. Yeah.
When we, in the member initialization list, when we do people curly braces, people curly braces person.
Yeah.
Why don't we actually have two curly braces? Because in my understanding, right, when you take a single curly braces,
I see what you mean. I see what you mean. Yeah.
Now we initialize, and then you actually have to pass proper array, otherwise that vector, which we don't do, right?
Yes. So what you could, so if you had person list, what is it? We've got something like that. I personally think it would have been nicer if you would say round brackets, and then inside there, we put a list. So this is saying, okay, initialize people with a list of person, right? That would make more sense.
It would make more sense because this is somehow under the hood. Something's going on.
Yes.
It's not really explicit.
No. All right. So this was something this initializer lists thing was for vector, etc. was added in C++ 11, and it has come to be regarded as something of a bad idea. Well, not a bad idea, but just kind of a bad implementation for reasons like you say, right? And for reasons of, well, now you have to know what kind of class you're initializing to know whether you have to use round or curly braces. And the idea, the goal of it was that you could just use curly braces everywhere, and it was going to be uniform initialization. You didn't matter whether you were initializing an aggregate or a class with actual constructors. You define constructors, and it's just turned out to be more of a mess than anybody actually intended. So I wish they had gone with something like this, but they didn't. And if you want to initialize people, the vector, as from a whole bunch of person objects, then this is the way you have to do it. It's just the way it is, I'm afraid. I agree that it's not intuitive, but there we are.
So the other thing wouldn't even compile.
I
haven't tried.
I haven't tried it, so I suspect it will actually, but it's certainly not kind of idiomatic. It's not something you see. I suspect it will work though.
Compiles.
Yeah. Well, that's good. All right. Let's go on to talk about something new. Let's go on to talk about destructors. Who knows what a destructor is? Kind of. Who knows what finalizers are? Okay, destructors aren't finalizers, so let's get that out of the way. Except when they are, but they're sort of not. Anyway, let's not talk about constructors, let's talk about resources. So about resource management. Okay, most of you, I think, probably already do some coding in other languages. Who has written code that looks roughly at a high level something like this? Acquire a resource, do something with that resource, and then release the resource. One person. One person's put their hand up. I reckon anybody who's done any sort of non-trivial programming has written something that goes like this. Are you going to say something like it?
Well, it's okay.
Acquire a resource, use it in some way, release it once we've finished. This is an incredibly common pattern. And there are many kinds of resource. The reason I've used the term resource rather than something specific like memory is because there are many, many kinds of resource that this is appropriate to. Memory is one, and the most common. Heap memory, free store, whatever you want to call it. But it also applies to file handles. How many times have you opened a file, read that file, closed the file? Right? A file is a resource. There are a limited number of files that your program can open. You don't want to keep a file open for longer than you need to. Network connections, for example. Open a connection, open a network to connect us somewhere, get some data from it or send some data to it, close the connection. Acquire, use, release. Mutexes, of course, if you've done multi-threaded programming. You definitely don't want to hold on to a mutex for a microsecond longer than you need to. Acquire, use, release. Now, yes, as I mentioned, the most common case for doing this is memory. And this is so common, in fact, that we have come up with an entire class of programming language, that the majority of programming languages these days are written so that they will take care of the release bit for you. At some point, the garbage collector is going to come along and release that memory once you're finished with it, right? And that's nice. You can just acquire something and at some point somebody else is going to come along and empty your bin. That's lovely. But it only works, in garbage collected languages, it only works for memory. You still have to worry, in general, about closing files once you finish with them, about closing network collections, certainly about unlocking mutexes.
Context managers in Python, so you kind of don't.
Well, Python's an interesting case because it actually uses reference counting rather than like traditional garbage collection, but that's a bit of an aside. The trouble with this pattern is that, yes, all right, the example on the board is 3 lines. That's easy enough. But as our program grows in complexity, it's very, very easy to make mistakes. That's one of the reasons that garbage collected languages exist in the first place. It's very easy to make mistakes. If you imagine that instead of do something with being one function call here, it was instead 1,000 lines of code calling lots of other functions in between, perhaps with several return statements, because it does error checking along the way. Yes, Michael?
Well, there's actually a very simple example when you try to clean up a binary tree. I've once tried it in C. It's very easy to miss one leaf. It's quite difficult to make sure that all of the nodes get cleaned up on the way.
Yes. I'm not sure that most people have written binary trees in C, but
Well,
yes.
Whenever you have a pointer who points to a pointer,
Yes.
it's very difficult. It's
A
very
linked
difficult
list,
to
which
miss
is kind of a unary tree, would probably be another example. But the point is, as our program grows more complex, this becomes harder and harder to manage. And in C++ in particular, this is problematic because of exceptions, because in general, we have to assume that any function call may throw an exception, and an exception, if it's not wrapped in a try block, is going to exit from the calling function immediately. We're just going to jump out of the enclosing scope. So if our do something with a function through an exception in this case, the release line would never ever be run. We would never release that resource. And that'd be bad. So this is really common, really hard to deal with, consistently, correctly, all of the time. How do we do it? Well, luckily for us, the C++ language provides tools to help us. And you've already seen and been using one of those tools and not even realized that that's what it was for. Because C++ has constructors. These are functions that the compiler automatically runs when we're creating a new object. And the counterpart to a constructor is a destructor. And a destructor is a function that is run automatically by the compiler when it is destroying an object. Constructors used for creation, destructors used for destruction. Right? Yeah.
Destroying an object can mean also destroying a class or structure, or just let's say a procedure or something.
I mean, like an instance of a class. So, like standard string is a class, and you can have multiple different objects of type standard string. Yeah. So when we are destroying an object, the standard string destructor is the compiler automatically calls that destructor.
That means it will be 0 or whatever the value, or the whole thing.
Well, hold on and I'll show you kind of what that means. So we've already seen constructors. They have a counterpart, destructors. And if we use these facilities, if we acquire a resource in a constructor and we release that resource in the destructor, then we can use the language rules of C++ to ensure that resources are always released exactly when we finished with them. Nothing ever leaks. We never attempt to release things twice, which is also quite a big problem. So instead of what I wrote before with these functions acquire resource and release resource, we have a class. In this case, I've called it resource handle. And now in our example function, we create a resource handle object. And we imagine that the constructor of this object is going to call acquire resource for us. We use the resource, do something with resource, just like we did before. And then when the example function is finished, when we leave the scope, when we reach this curly brace, the resource object is going to be destroyed. Its lifetime has ended. It is finished. It is an X object. It is shuffled off this mortal, whatever. The resource is going to be destroyed by the compiler. Its destructor is going to run. If the destructor function calls release resource, then we are automatically going to release the resource. We cannot possibly leak because it's the compiler's responsibility to call the destructor. Right? So we cannot possibly leak the resource in this situation, as long as we've written the resource handle class correctly. And it's even better than that, because now, if the do something with function throws an exception, we still get cleanup. Destructors still get called for us. So I know we haven't talked about exceptions in this class yet, but I know a lot of people will be familiar with them, and they work pretty much the same way in C++ as they do in most other languages. Right. So because we don't have an explicit try-catch, try-block around this do something with, means the exception would just bubble up through up to whatever called example. But because this is now an object, the compiler is going to automatically insert a call to the destructor of this object, whenever and however we leave this calling scope. And this pattern, acquiring a resource in the constructor, releasing it in the destructor, is pretty much the best thing about C++. I'm not lying. This is brilliant. This is absolutely my favorite thing about C++. It's why I use C++ rather than a whole bunch of other languages. It has a name. It goes by this silly acronym RAII, which is Resource Acquisition is Initialisation, is what it stands for, which is kind of really, really meaningless. And it also focuses on the wrong bits. Because to me, the acquisition is not the interesting bit. It's the releasing of the resource automatically that's the interesting bit. If I could go back in time and change the name and get people to call it something different, I would. I prefer the term scope-based resource management. I think that's more descriptive of what this is. But if you see the term RAII, I don't think people say it as a word, which is good. If you see the term RAII, what it means is this: acquiring resources in a constructor, releasing resources in a destructor, using object lifetimes to manage resources. And I say this is the best thing about C++. I'm sure a lot of you have heard of Rust, programming language. Well, Rust has really taken this idea as far as they can go. Like pretty much everything in Rust is about RAII. Right? They have recognized that this is one of, if not the best thing about C++, and kind of almost based a whole language on it. The C++ standard library actually provides some of these RAII scope-based resource handles for us. A couple of them you've already been using without really realizing that that's what they are. So a vector, for example, can have a variable size number of objects in it. The only way to do that is by using the heap, the operating system memory, because at the time you compile your program, you've got no idea how many objects might be in this vector. So what vector does is in its constructor, or when you, as you call pushback, it gradually resizes itself. It asks the operating system, can I have some memory please? Thank you. Places the objects in this memory. The vector destructor, when the vector goes out of scope, when the vector is destroyed, the vector destructor releases this memory back to the operating system. So vector itself is actually following this pattern, although you've probably never realized it. The same with standard string, which is very much like vector in a lot of ways. There's also, you've been following, if you have read a bit about C++, you might have heard of smart pointers. The idea behind smart pointers, and the most common one that people use is called unique pointer. The idea of smart pointers is that they use this RAII scheme to automatically free, release, destroy, delete objects when they go out of scope. That's what makes them smart. Right. So, as I said, the destructor is a special function which is run by the compiler. A constructor is an object is run when we create an object. A destructor is run when that object gets destroyed. And objects are destroyed when we leave the scope in which they were declared. And usually this means the innermost set of curly braces in which they appear. Right, as soon as control leaves that innermost set of curly braces, the object is destroyed. Its lifetime ends, it is destroyed. And what makes this so powerful, what makes it work, is that the compiler automatically inserts calls to the destructor no matter how we leave a scope. So imagine you've got a long function, 1,000 lines, and 500 lines in, there's a if so-and-so return, like return early, don't bother doing this stuff down here. Again, that's a very common thing to do. The compiler will automatically ensure that any live objects are destroyed no matter how we leave the scope. I've already mentioned, even when throwing exceptions, again, destructors are run automatically. In fact, there is no way to stop it, even if you wanted to, right? It's gonna happen. So, better make use of it. Start again. So I'll show you what I mean by this. Scope-based lifetimes. So here I've got a vector of strings. So lots of heap allocation going on here, probably. So this is a function that takes a vector of strings by value. And the first thing we do is we say, okay, if the vector is empty, just return straight away. Don't bother trying to do anything else. And if we leave the function here, then this vec object has its destructor run. Well, in this case, if the vector was empty, it didn't actually have anything to destroy, but still, the destructor is going to be called, because this object is in scope at the time that we leave the function. So now let's create a string. Well, we know the vector is not empty, so we can read the 0th element from it. Sorry. So we're going to copy it. We're going to create a new string object from whatever the first thing was in the vector. And now we've got two objects in scope. We've got str and we've got vec. And so again, if we leave the function, these two objects are going to be destroyed. In fact, we even know the order in which they're going to be destroyed, because things are always destroyed in the reverse order that they're constructed. So str and vec are going to be destroyed. In fact, they're going to be destroyed in that order. Slightly more complicated example now. Got a range-based for loop. So for each string in the vector, auto s in vec, if the string is empty, I'm going to break out of the loop. So this is a little bit trickier. But what happens here is that every time we run through the loop, the variable s, because it's not a reference, it's a value, the variable s is going to be initialized with a copy of the appropriate element from the vector. And when we leave this loop via a break statement, we are exiting the scope in which S was declared. So the break statement leaving the loop is going to cause S to be destroyed. Like I say, these rules are like airtight. There's no way around them, and that's good.
In this case, you're talking about the statement block, or like the outer curly braces, right? So after.
Yeah, and then the final curly, because this is the void function, we can just fall off the bottom of it. When the function finally ends, the final curly brace, the objects that are alive at that point are str and vec, so those both get destroyed at the end of the function.
I meant like the curly braces for the for loop or for the if.
Well, inside the if, there are no new variables inside the if.
Yeah, there's something.
So we don't have to destroy anything when we leave the if, although in theory, we could declare a new variable in here, and that would be destroyed when we left the if block. But break takes you out of the for block as well, which causes anything declared in that for block to be destroyed, and S is sort of morally part of that for block, even though it isn't literally inside the curly braces. So you've probably, if you've been writing C++ or related languages for a while, you've already internalized these rules, even if you didn't know it. Because you already know, most likely, when you can access variables, when that variable name appears. So for example, down here, underneath the for loop, you already know you wouldn't be able to refer to the object S, because outside of the for loop, that S doesn't exist anymore. Right? If you try to use the variable named S, the compiler's going to go, oh, what? There isn't one. And the reason is that because S only exists within this for loop. So again, if you've been writing Java or C# or whatever, you probably have already, you're already familiar with these rules of when, of scope controlling the kind of the access to names, if you see what I mean. And C++ extends that a little bit to say, well, it's not just that you can no longer get at that variable, it's that variable has been destroyed, its destructor has been called, any resources that it held have been released. So this says where destructors are going to be called. That's not much good if we don't know how to write a destructor. So let's have a quick example of how we actually go and write one of these things. Well, we write a constructor. A constructor has the same, it's written like a member function that has the same name as the enclosing class and no return value. Right. Something we've been doing for quite a few sessions now. And a destructor is the same, except the function name or the class name is preceded by this tilde character. You can think of it as like not. And like constructors, destructors don't have a return type. It is possible and usual and common for a class to have multiple constructors. However, a class may only ever have one destructor. We can't have multiple overloaded destructors. A class only ever has one destructor, and that takes no arguments. And if you think about it, that kind of makes sense, because calls to a destructor are done by the compiler, not by us. I mean, it is possible to manually call a destructor, but like, that's advanced stuff. By and large, calls to destructors are done by the compiler. And the compiler has no idea how this thing was constructed in the first place, doesn't care, it only cares about how it's destroyed. So only one constructor, and it takes no arguments. Constructor is a function. Function has a body, list of instructions. Once those instructions are executed, then the compiler will go forth and it will destroy each of our member variables in turn. In fact, in reverse order, from the bottom up. So inside the body of our destructor, all of our member variables are still alive. We can use them, we can inspect them, we can refer to them. That's fine. After the body of the destructor is finished, then the compiler goes ahead and runs the destructor of each of our member variables. In fact, this is the exact opposite of what it does when we're constructing an object. So, as I just said about half an hour ago, when we construct an object, our member variables get constructed in order, then the constructor body runs. With the destructor, all of that is turned upside down. The body of the destructor is run, and then the member variables are destroyed from the bottom up. Reverse order of construction. So here I've got a little example class. And we've got a default constructor, and the only thing that this does is print the word constructor. It's very exciting. And I'm sure you'll all be thrilled as to what's coming next, which is the destructor. So here, first one is a constructor, has the same name as the enclosing class, no return value. This is the destructor, has the same name as the enclosing class, but with this tilde on the front. So this is the function that gets run when we construct an example object. This is the function that gets run when we destroy an example object. As you might imagine, if we construct an example, it prints the word constructor. Yay. And then if we enter an inner scope and we construct another example, we're going to get the word constructor printed again. You might want to finish, you won't want to wait till I've...
Okay.
But now this is an inner scope. This is, I don't know if everybody knows you can do this, but you can open one. You can open a scope at any point inside a function. So this is an inner scope. And when this scope ends, this object ex2 is no longer accessible, it gets destroyed. The compiler is going to run the destructor for us. And so the word destructor will be printed. Okay, let's take this a bit further. We're going to construct a vector of example objects this time. This vector is going to hold 3 objects. So what do you think this is going to do? Yeah. So this is what I was saying, by the way, that vector does different things depending on whether you use curly braces or round brackets. In this case, I'm calling it round brackets. So I've selected a vector constructor that says, make me a vector of 3 default constructed objects, please. And so vec here is going to have 3 example objects inside it. Each of those example objects is going to be default constructed. So this is going to print constructor 3 times. We're going to have 3 calls to the example constructor. That makes sense? Yeah. We've all been a bit sheepish today. So now here's the question. What happens here? It's not a rhetorical question. I want answers, damn it.
Everything prints destructor 4 times.
So there you go.
Prints destructor 4 times.
Prints destructor 4 times is the correct answer. Yes. Because at the moment that we leave the function, well, we have 2 objects are alive, vec and ex1. ex2 has already been destroyed, that doesn't count anymore. So we've got vec and ex1. The compiler is going to destroy vec, and the vector destructor, in turn, is going to destroy its contents, and it's going to destroy each of the 3 example objects that are inside it. And after it's finished destroying vector, or vec, sorry, the compiler is going to go on and insert a call to the destructor of ex1. So in total, we've got 4 example objects alive at the point we exit the function, so all of those get destroyed. That's nice, that's great. This is the thing that garbage collectors do for you automatically. Right? Oh, you finished with it, oh, I'll get around to destroying it kind of one day, stop your program for several milliseconds while I think about it. No, not in C++. You finished with it, it's gone, there and then. Right? It's better. Not this waiting around, I might, do the hoovering when I feel like it. No. No. Your garbage is there is no garbage. Everything is freed exactly at the point that you have finished with it.
Is there any other advantage to this approach except for the speed? As for language?
Is there so apart from speed, determinism. What I mean by that is that, all right, I'm being a bit facetious with speed, right? Because actually garbage collection can be very, very fast. The JVM has an extraordinarily sophisticated garbage collector, right? Written in C++, I might add. But anyway, so it's not necessarily that it's faster, but it's that you know exactly when it is going to happen. If you're writing something like a game, right? You have 16 milliseconds to draw 1 billion polygons on the screen for the next frame. Right? The way garbage collectors typically work, not all of them, typically work, is that they sort of stop your program for a fraction of a second and kind of look around to see what they need to free this time. Like, it's a lot more complicated than that. And basically that introduces an unpredictability into the runtime of your program. If you're running a game, you need to know exactly when the garbage collector is going to do its work, because otherwise You know, you're not going to get your nice smooth frame rate, 60 frames a second, people killing each other in Fortnite, right? It's the reason, one of the reasons that games are typically written in C++ rather than in, say, Java or C# or one of these languages, or at least the heavy-duty, like rendering part of game engines. The other thing, the other reason that I say this is better is the thing I said right at the beginning of this section was that garbage collectors are great for memory. That's their job, cleaning up memory, right? Releasing it, handing it back to the operating system, conceptually at least. But memory is not the only resource. It's a resource, but not the only one. And this pattern, this RAI pattern, works not just for memory, but also for any other kind of resources that we might be using in our program, whether that's file handles or network connections or mutexes or whatever other kind of resource, scarce resource, that we absolutely must not hold on to for any longer than is absolutely necessary. And that's not something that garbage collectors, naively at least, can deal with. Sorry, you had your hand up for ages and I've just been ranting.
No worries. There was once a good talk about like that garbage collectors actually create a failed sense of safety, because what especially object-oriented languages do is pass around references to each other, which ends up in huge objects lying around the memory, which are not used anymore, but which never get cleaned up.
Yeah, so you end up with circular references. So this thing holds,
Or
look
linear
at
references.
keeping that thing alive, which is keeping that thing alive, and you've got 30 objects in a chain. And again, like really sophisticated garbage collectors can sort of see through that. But yeah.
Well, I mean, like one common problem that happens is when an object has reached a certain life length, how do you say, lifetime, that the garbage collector does not tend to pick it up anymore.
Yes. Yeah. I mean, it still does, but it might take many, many cycles before it actually gets around to destroying it. Yes. So, any more questions about either the concept of destructors or the syntax of destructors?
Yeah, kind of one. Do we, so I'm not sure if I understood correctly, but we write explicitly by hand destructors when we want to do something else on top of destroying the object. Is that correct?
Precisely, right. So, yes, when this is probably would have deserved a slide by itself. Yes. When do you actually need a destructor? And it's precisely when you say, what you say, is the compiler is going to destruct all of your member variables and base classes anyway, right? What the destruct, when you need a destructor, basically when you're doing this resource handling stuff, when you want something special to happen when the object is destroyed, right? And it is rare, I guess, or uncommon. Like most classes don't need destructors, is what I'm trying. Don't need explicit destructors like this. That's what I'm trying to say. But it is a very important pattern, and it's something that is a very useful tool and something to be aware of, which is why I'm telling you about it. But most classes that you write, you don't need to provide an explicit destructor. Nor were you going to?
Is it related to the type of memory you are using for the members of your class?
Related to the type of memory you're
If
using?
it's located on a heap, then you might have to write
Yeah, so what typically happens, and we're going to see this in a second, with heap memory is that you ask the operating system, can I have some memory? And it'll return you a pointer to some memory somewhere. That is the address of the start of this memory block that it is reserved for you. Right. And what you need to do is when you have finished with it, you say to the operating system, okay, I have finished with this lovely memory that you gave me, at this address. I have finished with that. Now you can go and use it for other purposes. Does that make sense? Yeah.
Because the curly bracket doesn't signify that instance that
Curly braces versus round brace. No, that's like a syntax thing, whereas destructors are more a kind of like a different concept. The curly versus round doesn't really come into this. Yeah.
So I'd like to ask if I'm right, destructors release memory when we don't need certain things.
Destructors can release memory. Destructors can do whatever you ask them to do.
Well, what does it mean really, destroying an object? I understood it's wiped out from memory to
So
get space.
I guess the point of these destructor functions is that it allows you to customize what destroying an object means.
Oh, I see. You're not necessarily making free memory, but
So typically it will be used to release resources, whatever that resource might be. But you can do whatever you like in a destructor. Here we've just used a print statement. Right? You can. In fact, I've seen some very innovative use of destructors, should we say? But you can do like theoretically anything you like, such as printing something out. But the typical use of destructors, and the reason that they have that name, is because it allows you to customize the tear down process for an object to do special things if you need. On the rare occasions you need to do special things, typically when there is some special thing that you have to take care of yourself.
We can say just not available means not availability, or how can I say? So the object is not available anymore.
No, once it's destroyed, it's gone. It has ceased to be. You cannot interact with that anymore. It is gone.
Like chucking a.
Yeah, gone.
I see.
All right.
Can you maybe just quickly point out in like a couple of seconds again, because you said at the beginning you're so excited about C++ and the out of scope.
RAI.
construction.
Yes.
What the difference is to Python, where you also have this out of scope garbage collector picks it up.
It's actually quite interesting in Python, because Python doesn't have a garbage collector in the same way that say Java does.
Right.
So or at least the CPython implementation, the usual implementation, actually uses reference counted objects. And so what happens is that when an object's reference count reaches 0, then the object is destroyed, which is kind of, I suppose, a simple form of garbage collection, but it actually has far more determinism than something like the JVM garbage collector. Right. So yes, in Python Python also has finalizers, which are these functions that get run when the object, similar to destructors, when the object is destroyed. So you can do things like closing a file in the finalizer in Python and rely on that. Whereas, yes, you could do that in Java or C#, and they do, but you don't know, in Java it might happen in 2 seconds time, which might be far too long. You definitely don't want to hold on to like a mutex or something for 2 seconds. That would be terrible.
So,
Yeah.
so basically, from an average user's point of view, there's very little difference. It's more like an implementation detail in some sense. No? Like if you're a C++ expert, you admire the thing for its beauty. But if I'm just my regular data scientist doing my coding,
Regular data scientist doing your regular job.
but then do it really, for me it's like things go out of scope. Okay,
They're gone.
they're gone.
Yeah.
So.
That's it. That's the whole
so
concept.
you would agree.
That's the whole concept.
Yeah.
That's,
Yeah.
Yeah. Michael.
Well, I mean, of course it's like meant to be a semantic thing, but you can actually use it against itself, especially in Python. For example, in Python, whenever you create an object, let's say a number, if you create two variables which both have the value of 2, and they actually point to the same object, although they were never created together at one point. And because the identity of the object is different than the actual object in memory, or separate from each other, you can actually find ways to write a value into that object so that it will how should I say, become a new identity, but always treated as the old one. Let's say, for example, you overwrite the value of 2 with 4, and then whenever you're trying to count, the computer suddenly starts to count 1, 4, 3, 4, 5. There's an interesting article on that.
Alec.
Tristan, probably correction. I just double checked. It looks like Python has a garbage collector which does market sweep. They expose the whole API to do like find the
because I know it has circular reference detection. So
yeah, and that's already a property of like market sweep thing, I guess.
okay, well there you go. I was wrong.
But
Python's more sophisticated than I gave it credit for.
But still, like from the point of like widely used languages, one example I guess is Objective-C, where people are used to reference count and
Yes,
like
team release. Swift actually uses reference counting for its classes. Structure value types like in C++, but classes are reference counted in Swift because it's got so much in common with Objective-C. Yes. And it's possible to do automatic reference counting in C++ as well. There's another kind of smart pointer called shared pointer, which basically does reference counting for you. But you should probably not use it as often as people do. Anyway, of course I've told you about destructors, so of course now I want you to go and write some destructors. Or in fact, one destructor and one constructor, please. Slightly differently to how we've done exercises, because I've given you some starter code for this one. And if you go to that URL that's on the screen, you will see, hopefully, fingers crossed if I've done it right, the README file will pop up in GitHub. What this contains is an example of what a very simple C library might look like. So this, well, the C libraries almost universally use this pattern of providing you with a function to construct, to acquire a resource, to construct something, several functions usually to use that in various ways, and then a function to free, destroy, release, whatever, the object. Exactly this acquire, use, release pattern that we talked about right at the start. Right, because C doesn't have constructors or destructors or any notion of that. So what I provided you is basically a very simple example of a C library. And of course C and C++ can call C libraries very happily. So what I want you to do is to basically write a nice class, a resource handling class around this C API. So take a look at that. If you need help cloning the code or anything like that, I'll be munching donuts at the back.
Just wondering, so for the scope you showed just now, is the only use case kind of guarantee anything created within the destroy?
Yeah.
Is that only use case?
That is why people use the inner scopes. Yes, it's just so you can have a bunch of variables. So yes, it's so you can have a bunch of variables that kind of destroyed early in the function, don't last till the end of the function. Yeah. I wasn't kidding about the munching donuts. Thank you, Tom.
copy it, right?
Just copy it to the address bar.
Oh.
It's not a search term.
So don't worry too much about what's going on in the memory resource header file. It's just deliberately complicated functions. There will be not really, but yeah, don't worry too much about what's going on in there. Just use the functions.
I've done it here, but I don't know.
It's not a search term. Use it as just a normal app. Where are you? Have you ever searched this one?
This one.
Computer.
Thanks.
Oh, this is Alex, by the way. Say hello. You're going to be. He's going to be here in 2 weeks' time.
Yeah, so next time, like, is it the last class?
This is the last one for this. Yeah. Don't worry, it's going to be great.
STL. You'll be telling us about the details of STL.
Yes, this is a small teaser of what's coming in 2 weeks. Like the next module is going to be about getting to know the C++ standard library, and trying to give like a brief introduction and lesson about it.
Does it make sense? Do people understand what I'm asking you to do? It's okay if not. It's okay if it is. Or I'll just find the silence often.
Can we run the code to find the bug, or do we have to find it before?
Or run the code and see what happens. Of course you can.
Does it explode itself? I didn't look into memory resource.
Bug is not your memory resource.
No, I know, but like what happens when you basically don't relate it?
There was a nice REST article called Crash and Burn.
Hmm?
There's a nice REST article on that called Crash and Burn.
About related resources or?
Like, it was actually about unwinding the stack. Like, do-it-yourself meta operators, exactly. Like the difference between abort and mind.
Mm. But here, like, I'm afraid we are not gonna support it. So there is a bug. But the fact that we
Yes.
don't release it,
That's definitely.
it's not gonna explode or something.
No, that was supposed to be.
Yeah, therefore, like, it's just like, I was wondering if people just run it, it's gonna run smoothly.
It's gonna work absolutely fine. Yeah, that
Yeah.
was the idea. I was trying to prove the point that this is hard to get. You know, it's easy to overlook because it can run correctly, and unless you run it a million times, you're probably never going to notice that you're doing something wrong. Because if you can overlook it in like a 10-line function, imagine a 1,000-line function. How hard that is to get right.
I can have a look at a 3-line function.
Yeah.
How many people have been able to run the original code? Yeah, just like grab it and run, so like.
Yeah, it should just compile and run, because the CMake project should be able
So
to
like I
import
can
it
search
straight
how
into
many,
CLive.
like how few hands I'm seeing so far.
We just need to copy and paste in CLion.
Well, you can clone the project. So if you look on the page in the top right corner,
And this one.
oh, you can copy.
But
if
we
you-
have to include this one.
Yes, if you go back to you can clone or download. You can, if you like. It's
Yep.
very easy. Just download the zip.
Yeah, just we have to unzip it. Okay, so these are files that are inside it, so you just got to unzip these. So you can copy those wherever you like. Those are the files that are inside. And then you should be able to open that project in CLive. You got it?
that's probably a limitation of my hardware at this point, because it doesn't seem to compile on paper.
Oh yeah, no, that's.
Whatever that means.
Yeah.
That's weird. I'm not sure quite what I did to trigger that. So France are going to win then?
Well, we're still getting few tries. Mistakes and reversal of score, like equal 0, then some players are slowly appealing. Enough to use Filipinos. And then the winker on the left. No, the other.
And if you go
One
back
was
on the
very
page,
steep
you also
or-
will be able to find
He's out, but
choice of content is the way that you upload the content. And if you look for course material initial or something,
I think the one who's
you'll
got
find
the
similar
first
slides for the previous. I think it was sort of like and basically
this
initial investors. And you will be able to do
his defense is he doesn't know what position to send. And he should have the first ball.
Well, he's very good at when he does have the ball and running past people through the.
This is the same as last team.
Yeah, it's true.
But you see that you'll see if you're going to
8 5
5 or 6
5
Yeah, well, France, the defence was very, very good against England.
Yeah.
I know we scored 2 tries, but that was just Johnny Napier. Apart from him, we didn't look like scoring.
So
But yeah, against Italy, it wasn't
yeah, I
quite.
think the end session, the next one will be
Italy was
Yeah.
next week Tuesday is Christian
Well,
doing
try
the
it.
initial course in 2 weeks.
Very
This is
strong.
the last one.
It's in the start on the line.
Yeah, yeah.
Here you got the possibility. You see this first the way the rules are.
In 2 weeks.
It's very strange.
You know what I mean?
Will you just ask me a question, like, when you turn this around, you're just interested in
Once again, no, I work for like sports analysis company, they have zero interest in sports.
Oh.
Yeah.
Okay.
And then we sort of like
Plan.
No, I don't pretend, just I don't care what this thing is about, anything else as well.
Just numbers.
Yeah, just numbers.
What kind of sports?
No, 25th of teaching this.
It's huge.
And I will be doing it also every 2 weeks.
Surprisingly.
Watching 2 days, so 1 Tuesday is Christian.
So except one first player like Rose.
Yeah, I don't know, I think that's some bandit.
Yeah, it's some
So basically, the year I want you to modify the function use resource example to do exactly what it does now, but without the bug.
How many initial classes have you done from the other chapter to the chapter?
2.
So the third will be
Next week.
Can't find the bug.
Okay. What is the pattern we are trying to Who can see the bug in the initial version of the use? What do I call it? Use resource example function.
Yeah.
Who has spotted the bug in this? It's too hard. Okay.
Well, it is.
What is the pattern that we are trying to? The pattern I was talking about: acquire, use, release. Right. We need to make sure that the resource is released, however we exit the function. So how many different ways are there of exiting that function?
Two ways.
2 ways. On how many of those paths are the resources correctly released?
One.
Something I don't understand here. I don't think that this should be, am I right? Is it this?
What's the problem?
Is it the right part what I initial?
That's the bit that's the function you should be looking at.
If I,
Okay,
why do I get that?
Okay, so let's-
No? Still loading,
it is apparently still loading the CMake project. There we are. Right. Okay, good. So now if we press play. There we are. That is exactly what it is supposed to do. So here's the code. Nothing to worry about. So there is something wrong in this use resource function, use resource example function.
Basically it does something which we expect, but there's something strange happens.
Yes. I made a mistake when I wrote that function. Bad me. How could I? Well, again, I wrote one on purpose. There might be others that were unintentional. I wrote one I know about. If you find any others, please let me know. I was kind of worried when Alex said, "Oh, I can see a bug in this," but I was like, does he mean the one that I meant it to be there, or yeah? Okay, I might actually just put this up on the board. Oops. Why is that? Okay, this is rather huge, isn't it? Let's take it down a little bit. Okay, so this was, I'm not going to go over the answers now, but just to give you a little bit of a hint. So this is the function that we are looking at. Bump it up one more. There we are. This use resource example function. So this is, we imagine that we're taking our like C library that has these acquire, access, and release functions, and we are just using that from our C++ code. Like really, really common thing to do. There are thousands and thousands of C libraries out there. They most often provide you with functions that look roughly like this. So this is following the pattern that I showed right at the beginning of the lesson. We are acquiring something, we are using it, and then we're releasing it. Acquire, use, release. All good. Except there is a problem. So what is the problem?
If we talk about destructor, the sign should be somewhere.
I'm sorry?
If we talk about destructor, the sign for destructor should be somewhere.
Yes, we don't have any destructors yet. We haven't written any classes with destructors, so we don't have to worry about destructors just yet. First of all, we just want to identify what the bug is in this function.
We have to release the resource.
We have to release the resource. We are releasing the resource. Look there, line 20.
But if you are throwing an exception, if the index is out of bound.
Yes, that's a very, you've gone and looked at the header file, but yes. The rather more obvious problem occurs on line 17. So we can leave this function early. If the total that we get is less than 100, we bail out of the function early. We return 0. On line 17 here, we leave the function without releasing the resource. Right? This is a memory leak. And in fact, I deliberately called the function 7 times just to be really nasty. So we're leaking memory 7 times. And you can imagine, perhaps we called it 700 times, and this starts to actually matter, right? This is like a 10-line function, and it's got this bug, and it's not easy to spot in a 10-line function. So you imagine that this is like 1,000 lines. Not that you should probably write 1,000-line functions, but you know, people do. Even 100 lines. This is really hard to get right. In this case, we're only looking after one resource and we got it wrong. There are functions where you have to use multiple resources at one time, and you have to make sure that they all get freed when you leave the function. And there is, as Laurent said, another, which was a little bit nasty of me actually. There's another issue that you won't hit, but you might do if you edited this function, which is this access resource function will actually throw an exception if you ask for an index that's out of bounds. So if you ask, if the size was 10 and you ask for index number 20, then access resource is going to throw an exception, which is not in itself wrong, but it does mean that, again, the resource, the release resource function would not be called. If, on the other hand, we followed what I asked you to do in the exercise, and we wrote a wrapper class, a resource handle class, which released the resource in the destructor, this bug that is on here is literally impossible. Right? There is no way whatsoever that we can leave the function without destroying, without the destructor being run. And if we had multiple resources, well, the same would apply, because the compiler is going to insert destructor calls for all the variables that need it, effectively. Right? So it doesn't matter if we had one resource or 10. They're all going to get destroyed. However we leave the function, whether we leave the function here, whether we leave the function at the bottom, whether we leave the function because something we're calling through an exception, it doesn't matter. If we use a resource handle, we don't have to worry about it anymore. So this was a bit more complicated an exercise than I have given you in the past, because we're growing up. We can handle things like this now. But part of the reason that I wanted to give you something with some actual real executable code as opposed to just some lines on the board was because I wanted to show you just how easy it is to make these mistakes when using these acquire and release functions. This is me kind of getting on my high horse and proving a point to you. This is like 10 lines and we got it wrong. This is how hard this stuff is. And it all goes away if we use RAII. And so that is what you should do. You should use constructors and destructors to manage your resources. Now, we are pretty much out of time. Alas, that is it for this module. That is it from me to you for the time being, at least. So as I say, Alex is going to be standing in my place for the next few weeks, but it's been a pleasure. Thank you all very much. The solutions to this exercise are on the GitHub page. I don't want to go over them now because I think this is a really, really valuable lesson to kind of get used to doing this thing of using constructors and destructors, right? So I think if you have the time to do it, I would really encourage you to go and work through the exercise and get it working and see that, okay, well, now we're not leaking things anymore. This is good. But if you do want to look at the solutions, where are we? The solutions are on GitHub. There's a little drop down. You can select, there's a solutions branch, solutions EX1, or you can, or that's the URL if you want to go to it directly. Probably easier to do it from the first page. There is a bit more we would have gone on to talk about if we had time, because constructors and destructors are very closely related to copy constructors and copy assignment operators. These things generally go together, and if you write a custom destructor, more often than not, you need to customize the copying behavior of your class, either by preventing copying at all, or by inserting some custom behavior. And actually, you will already have seen in the README exercise 2 does go on to ask you to write a copy constructor. And if we had a bit more time, we would have gone on to talk a bit about copy constructors. So I will put that material on the slides, and again, I encourage you to go and read on the internet or textbooks if you have them about copy constructors, because they really do tie in very closely with destructors as well, and this idea of resource management. Okay, but yes, that's it from me. Thank you all very much. I will be here in a couple of weeks, but I won't be here, if you see what I mean. So, yes, that's it. Thank you very much. Cheers.